All right, today I'm going to be going over permutations and combinations. And basically what I'll be doing is I'll be telling you the difference between the two. Um, and then I'll be deriving the formula for each of them using a specific example. I'll take a specific case and then I'll generalize it for each one. So let's get started. Combinations. I'll start with combinations first. The definition of combinations. A combination is a collection of objects. It is a collection of objects and not an arrangement of objects. I emphasize that because a permutation, I'll explain it later, but a permutation is an arrangement of objects, whereas a combination is just a collection. All right. So just an example of what may be considered an object. I know we don't typically think of people as objects, but in this case, people are objects. People, phones, cars, etc. A noun, anything that's a noun, a person, place, or a thing can be considered an object, and therefore it can be counted. If it can be counted, it can be considered an object. An example, this is the specific example that I was talking about. 5 siblings: Jesse, JC, Jania, Janae, and Takia. You thought it was going to be another J name. Nope. I don't know why our parents decided to give her the only name that didn't start with a T. She's actually the oldest. So maybe I don't know. These are my siblings, by the way. I'm Jesse. JC is my brother. Jania is my sister. Janae is my sister. And Takia is my sister. She's the oldest. So I guess they decided they wanted everybody to have J names after they had her, which is kind of, hey. All right, so 5 siblings. We got 5 siblings, and this is the dilemma that these 5 siblings, we are faced with. We have a family vacation, but one must stay home. One of us got to stay home to watch the dogs or something like that. Feed the fishes. We don't have fishes, but just an example. So, how many combinations of siblings can attend the family trip? And in this case, this specific example, I chose something that'll be a little easier for us to actually count out the total number of combinations. I chose something that'll be a little easier, but as you can imagine, if you don't believe me, you could take my word for it. It definitely gets a lot tedious to count out all the different ways and combinations in which you can select from a group of objects. But in this case, I chose to go with something a little easier. So we have combination number 1. Okay, purple stays home. Oh, let me go back. Notice that I color coded each one of the siblings' names. I colored mine with black. JC is red. Jania is pink, yellow, and then we got purple. You don't have to remember which name corresponds to which color. Just remember that each color is a different person. That's as much as you need to remember. So we got the trip column, and then we got the home column. So this is one combination. 4 of us, black, red, pink, and yellow, go on the trip while purple stays home. Here's another combination. Black, red, yellow, and purple go on the trip while pink stays home. Yet another combination. Black, red, purple, and pink go on the trip while yellow stays home. And then a 4th combination. Red stays home in this combination. And then a 5th combination. Finally, it is me who stays home. This is the most realistic case right here. I usually get left on the family vacations. Oh well though. All right. But so in this case, it was pretty easy to count out the total number of combinations because for each combination of 4, it was the same as choosing a combination of 1. If I select 4 people to go on a trip, I'm really just selecting one person to stay home. Well, how many different ways can I select one person from a group of 5 people? Well, that's pretty easy. You can select person 1, person 2, person 3, person 4, or person 5. If you got 5 people, there's 5 different ways to select one person. But in most scenarios, it's more so like you're asked, you got 20 different objects and you asked to select a combination of 7. Selecting a combination of finding out the number of ways to select a combination of 7 from 20 total objects is extremely tedious, and that number is pretty large. I'm pretty sure it's more than 1,000 different ways that you can select a combination of 7 from 20 total objects. So that's the motivation behind wanting to come up with a way to come up with a formula for counting combinations, as opposed to wanting to brute force our way through picking and selecting and figuring out each different type of combination that there is. So moving forward, note one thing that I want you to notice. I do want to emphasize this. Notice that each one of these combinations, no matter the arrangement, each one of these combinations is considered the same combination. These are all the same combination. These are all the same combination. These are all the same combination. No matter how you arrange it. Notice in this one right here. And this one right here, black is first. Red is second. And then purple and then pink. In this one, I rearranged red and black. Kept purple and pink in the same order. And in this one, I rearranged almost everything except for purple, I believe. Oh, and black. I rearranged red and pink. It doesn't matter how I arrange these 4 people. This is all considered the same combination. That is the difference between combinations and permutations. In permutations, these would all be considered different permutations, different selections. In combinations, these are all the same selection. I shouldn't use the word selection for permutations. That's usually reserved for a combination. Permutation, the word that's usually used with permutation is arrangement, which makes sense. These will be considered different arrangements. That's one arrangement, that's another arrangement, and that's yet another arrangement. But they are all the same selection of people. And that is the difference, once again, between permutations and combinations. All right. In combinations, order doesn't matter. 3 exclamation points, because it really does not matter what order you take the same combination in. It is the same combination. So, in permutations, now we just got through talking about combinations. This is permutations. In permutations, a permutation is an arrangement of objects. It's an arrangement of objects. All right. Not a collection, unlike combinations. A combination is a collection, permutation, arrangement. Think combination, collection. You got a little bit of alliteration going there. So that'll help you remember. All right. An example of a permutation. I'm going to use the same 5 siblings. And I'll give you a scenario that is an example of permutations, of us using permutations as opposed to combinations. All right. So you got 3 siblings, and these siblings are to be seated in a minivan. These siblings are to be seated in a minivan. All right. Let's say they're going to the store or something. Who knows? And only 3 of them want to go, or only 3 of them can go at the time. So look at what we have here. All right. So you got seat A, you got seat B, and you got seat C. Notice that we have black in seat A, red in seat B, and then yellow in seat C. Notice here we have a different arrangement of these same three siblings. It's the same combination of siblings, but it's a different arrangement or a different permutation of these three siblings. Okay? All right. So in this case, we got red in seat A as opposed to in this case where we had black in seat A. All right. Moving forward, I think I stressed the difference between permutations and combinations enough. All right. So the question is how many different arrangements or permutations are there of, if we have these five siblings and we have three seats, how many different possible arrangements, how many different possible ways can we arrange three of the five siblings within those seats? Okay. So right here, what I have, this right here. That's one arrangement. All right. This right here is a different arrangement. Same combination, different arrangement. All right. This one right here is a different arrangement, a different permutation. Okay. All right. And then we do this and we keep doing that and we figure out all the different permutations. And it turns out that there is 60 different permutations, a total of 60 different permutations. Now, at least when I was first learning this, 60 seemed like a pretty large number. I wasn't expecting if you got five siblings and you just need to arrange three of them, I wasn't expecting that there would be a total of 60 different ways to arrange them. But there is. And as you can imagine, who would want to, if we needed to know the number of arrangements, who would want to actually have to sit here and write out each arrangement? 60 is already too many. But when you got 20 different objects to choose from, 20 different siblings, that's a huge family. If you got 20 different siblings to choose from, and you want to seat three, that's already more than 1,000 seating arrangements. If you have to count that many out, you'll be counting all day. It'll take you a minute. It'll probably take you more than a day. So that's the motivation behind us wanting to find a formula for ways to count permutations. And so one thing, again, I want to stress, notice that order does indeed matter. The order does matter. It does matter. Whereas in combinations, the order didn't matter. All right. Moving forward, permutations versus combinations. Once again, the arrangement, permutations is the arrangement of objects, whereas combinations is the collection of objects. All right. Now, how do we count? How do we count them? How do we count permutations? First, that's the one I'll go over first. It turns out we'll figure out how to count combinations using what we learn in how to count permutations. Okay. So first, permutations. All right. Just to recall, we got five siblings and we got three seats. And I wanted to know how many ways I could seat those five siblings. I can seat three of those five siblings. All right. All right. So I had seat A, I had seat B, and I had seat C. Okay. Now for seat A, think about it. How many siblings? I kind of gave away the answer. I accidentally let the 5 pop up. But imagine you don't know that just for a split second. How many different siblings total do we have? How many different total choices do we have to select for seat A? Well, there's 5 siblings, so we got 5 choices. Whoops, giving away all the information before we even get to it. Okay. Well, now we chose one. We chose one for seat A. And now how many does that leave us? How many siblings does that leave us? That leaves us with 4 siblings. Okay, so now we've chosen seat A, who sits in seat A, and we've chosen who sits in seat B. Now how many is left to sit in seat 3? Well, we have 5 siblings. 2 of them are already seated, so that leaves 3 of them left to be seated. So, boom. 3 siblings left. 3 choices left for seat C. And what do we do with these 3 numbers, 5, 4, and 3? We are going to multiply those 3 numbers. So that's what we do. That's how I figured out that there was 60 different seating arrangements. Now I'll explain why I multiply as opposed to doing some other operation like adding or dividing or something like that. Let me go back. All right. So the reason that I multiplied these three numbers together is because all right, let's think about it for a second. For CA, I have 5 choices. 5 choices to choose from. 5 choices. I have 5 total choices. 5 options to choose from who sits in seat A. And each one of those 5 options, let's say I choose sibling red, the red sibling. Each one of those 5 options, it produces 4 options for seat B. Okay, so if I chose red, just in a specific example, if I chose the red sibling, I still have the black sibling, the purple sibling, the yellow sibling, and the pink sibling left to choose for seat B. All right. So each one of those 5 options for seat A produces 4 options for seat B. So 5 options produce 4 options each. Repeated addition. That will be a total of 20 different options for whoops, what is happening? Okay. All right, cool. That'll be a total of 20 different options for how we can arrange. It'll be a total of 20 different arrangements. I'm sorry. 5 options for seat A produces 4 options for seat B. Each one of those 5 options for seat A produces 4 options for seat B. So 5 times 4, that's a total of 20 options or arrangements for how we can arrange the siblings for seats A and B. And each one of these 20 arrangements produces 3 options. It produces 3 options for who we put in seat C. Okay? And that's how we get 20 times 3. 20 times 3 is equal to 60, or 5 times 4 times 3 is equal to 60. So, moving forward, in the general case, we don't want just specific examples, because your homework, or in real life, when you're presented with a problem, accounting problem, you're not going to necessarily be presented it's not going to be presented to you as siblings in car seats or something like that. More realistically, it'll be I don't know, it may be people you may be trying to count. You may be trying to count the different ways that you can arrange them at a table or something like that. But whatever the case, we don't want a specific example. We want to be able to generalize this. So that's what we'll do. Let's make N the number of objects to choose from, and then let's make K the number of objects we must choose. So going back to the example with the 5 siblings and the car seats. Oh, wait. All right. Going back to the example with the 5 siblings in the car seats, N would have been 5. There were a total of 5 siblings to choose from. 3, K would have been, or K is 3. K would have been 3 because the total number of siblings that we had to choose to sit in the seats was equal to 3. So now let's figure out the total number of permutations. The total number of permutations is denoted by this right here. P, open parenthesis, N, comma, K, close parenthesis. P, N, K. That's usually how it's just said. Or, yeah, that's usually how it's said. All right, so P, N, K. What did we do? We did 5 times 4 times 3. I should introduce some notation here real quick before I explain further. So n factorial, or let's say a factorial. A factorial is equal to a times a minus 1 times a minus 2 all the way down, and you just keep multiplying all the way down till you get to 1. Okay, so just a quick example. I'll do 4 factorial. 4 factorial is equal to 4 times 3 times 2 times 1, which is equal to 24. All right, cool. So moving forward. What do we have? All right, so PNK is equal to n factorial. PNK, the total number of permutations when you have n objects to choose from and k objects that you must choose, is equal to n factorial over n minus k factorial. All right. That may, now, this the way that I wrote, now, earlier, I just wrote 5 times 4 times 3. N was equal to 5. How did I get from that to this? I'll show you. Just so that you know that that I'm not just, coming up out of nowhere with stuff. All right. So earlier, 5 times 4 times 3. Right here, I'm about to show you that 5 times 4 times 3 is equal to 5 factorial divided by 3 minus k factorial. Okay. Five factorial divided by 5 minus 3 factorial. Okay. So what is 5 factorial equal to? Is equal to 5 times 4 times 3 times 2 times 1. And what is 5 minus 3 factorial equal to? Well, 5 minus 3 is equal to 2. So that's 2 factorial. Well, what is 2 factorial equal to? That's equal to 2 times 1. Okay. So 5 times 4 times 3 times 2 times 1 divided by 2 times 1. The 1's cancel. The 2's cancel, and we left with 5 times 4 times 3, which is what we started with, which is what we had the first time in the example with the 5 siblings. All right. This is me explaining that all over again. When I did the notes, I forgot that I had explained it in the previous slide, so we'll ignore this. All right. So next, what I'm about to do. Next, I will be I'll be explaining combinations. Okay, I'll be explaining the formula of how we get how I'll be deriving the formula for combinations. Now, recall, this is the formula for permutations. Okay, we know how to find permutations. Now, we don't know how to find combinations just yet. Which it may be. It's not that bad. Finding the formula for combination. Here, let's go through it. So, recall the 5 siblings: yellow, black, red, pink, and purple. Now, remember when I was trying to figure out the number of permutations, When I was trying to figure out P, N, K in this specific example, P53, the number of permutations when I have 5 siblings to choose from and I must select 3. When I was trying to figure that out, a way that I could have listed all the possible permutations, what I could have done is I could have selected a unique combination, and then with that unique combination, what I could have done was, What I could have done was permuted or rearranged that specific combination over and over and over again. And then once I exhausted the total number of permutations for that specific combination, I could have went to a different combination and did that all over again, exhausted the total number of permutations. So look, in this example, right now, I chose the combination red, yellow, black. Okay. All right. So this is one permutation. This is a different permutation. Same combination, but a different permutation. And overall, a different arrangement. Same combination, a different permutation. Same combination, a different permutation. All over again. Keep doing that. All right. And then it turns out that there's just 6 different permutations of this combination. Remember, we found that there was a total of 60 different permutations earlier. And this combination produces 6 of that 60 different permutations. Okay. Now, I'll just rewrite just so that I'm just writing out the colors right here. Now let's move on to a different combination and let's permute that as many times as we can. Okay. Earlier, the last combination that I chose was red, yellow, and black. This one I'm choosing yellow, black, and purple. Okay. A different combination. The last combination included red. This combination includes purple. All right. And I'm going to permute this combination as many times as I can. Turns out it's just 6. I'll show you where that number 6 comes from. And then I do that all over again. Pick a new combination, and then permute that combination. And then I do that all over again. Keep picking combinations, and then I permute that combination. Pick a specific combination of 3 and permute that combination of 3. All right. So notice that there's a relationship between permutations and combinations. That's important. I do that over and over again, pick a combination, and I permute the combinations, and I end up with 60 different total permutations. Okay. All right. Here is the relationship between permutations and combinations. Notice that the total number of permutations is equal to the total number of combinations times the number of permutations within a combination. Okay. The total number of permutations is equal to the total number of combinations times the total number of permutations within that combination. So going back to this example, the total number of permutations within each combination here, let's say the combination black, red, and yellow. The total number of permutations within these three selected siblings is going to be 3 factorial. 3 times 2 times 1, which is equal to 6. Okay. So let's use that fact. The total number of permutations is equal to the total number of combinations times the total number of permutations within each combination. All right. I know I'm being really repetitive, but I promise you, in my personal experience, my most repetitive teachers, when it came time for exams or when it came time for me to apply these things to real world circumstances, I actually remembered it. Even though it was kind of annoying, I had one teacher who her voice wasn't I wasn't the biggest fan of her voice. But when it came time for me to use the material that she taught me, her voice was in my head reteaching me the material. And, as a result, I was successful in accomplishing whatever task I was presented with, in which I had to apply the material that she taught me. So, moving forward, we already know the formula for PNK, and we just found that. Oh, 1 second. Let me go back and let me introduce some different notation. Let me introduce this notation. Combinations. Combinations is denoted as CNK. This is saying the number of combinations when you have n objects to choose from and you must choose 3 of them. This is how you denote that. Okay. So, combinations. We found that the total number of permutations is equal to the total number of combinations times the total number of permutations within that combination. Okay? I'll go back to the example with the right here. I'll go back to this example. All right? The total number of permutations within this combination, we have three spaces. Space A, B, and C is 3 factorial, or 3 times 2 times 1. All right. Moving forward again. All right. So we know that the total number of permutations is equal to the total number of combinations times the total number of permutations within each combination. All right. Doing a little bit of algebra, we go from up here to down here. All right. Just doing a little bit of algebra, just by applying some algebra. We see that if we divide by k factorial on both sides, we see that C in k is equal to P in k over k factorial. Now, just to recall what we just did, we found the formula for not a recap just yet. What we're going to do is continue to derive the formula of CNK. We found that CNK was equal to PNK over K factorial. Well, what is PNK equal to? We found that earlier. PNK is equal to this right here. Cool. So let's use that. CNK is equal to PNK, or CNK is equal to PNK, which is this right here, divided by n minus k factorial. Divided by k factorial, which is this right here. And then we do a little bit more algebra and we find that CNK is equal to n factorial over n minus k factorial times k factorial. All right. Now, just to show you, and then we also know that PNK is equal to n factorial over n minus k factorial over n minus k factorial. All right. Just to show you that our formula for combinations work. Earlier, let's go back to the example that we were talking about with combinations. In that example, we wanted to what did we want to do? We wanted to pick a combination of 4 siblings to go on a vacation. We had 5 siblings to choose from, so n was equal to 5, and we had 4 of them to go on the trip. We had 4 to choose. Oh, whoops. we had 4 to choose. So n was equal to 5, k was equal to 4. And we found that c is equal to n factorial over n minus k factorial times k factorial. And let's see if everything worked out. Remember earlier we found that there were 5 total combinations. So let's see if that's the case. 5 factorial divided by 5 minus 4 factorial times 4 factorial. Well, what does that reduce to? That reduces to 5 times 4 times 3 times 2 times 1. All of that divided by, here, I'll get rid of this. All of that divided by, what do we have? 4 factorial. Whoops. 4 factorial times n minus k factorial. 5 minus 4 factorial is just, that's just 1 factorial. Okay. And what does that simplify to? Here, let's go to a new slide. What does that simplify to? That simplifies to that simplifies to, here, I'll write it up here. I'll write the simplification up here. So I'm kind of going back and forth between this top and this bottom. Hopefully that's not too confusing. So that simplifies to, let's see, this 1. Oh, I made a mistake. Here. 4 factorial is equal to 4 times 3 times 2 times 1. So this shouldn't be here. I accidentally put that factorial right there. All right. And 1 factorial is just going to be 1 factorial. So, 1 factorial is equal to 1. So we get 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 1. That cancels out, that cancels out, that cancels out, that cancels out. And all we left with is 5 over 1, which is equal to, drum roll please, what is 5 over 1 equal to? It is equal to numero 5. 5 over 1 equals 1, which is what we got earlier. We found that the total number of ways for one person to be left home, aka the total number of combinations of 4 people to go on a trip. Oh, whoops. It's not equal to 1. 5 over 1 is equal to 5. I don't know why I wrote 1. All right. So we found that earlier that that the total number of the total number of combinations amongst 5 siblings, if you had to choose 4, was equal to 5. And so our formula works. There is the formula, just in case you want to take a final look at it. That is the formula, and hopefully I was able to help you understand it. And yeah, good luck to you. Good luck in your educational endeavors. Thank you. Peace.